Welcome back, and let's talk about floats. Every now and then I run into a programmer, professionals, that don't actually know what a float is. Okay, they know that 0.1 is a float, except 0.1 isn't a float, it doesn't exist. But it becomes more and more frequent that I encounter people that don't actually know how floats works. So I think it's important that we talk about it. As an example, let's take a look at this. What happens here if I run this code? Do we run infinitely? So let's go through the code first. We create two variables and we flip-flop between them. And in an infinite loop here, well, presumably infinite loop, while previous is not equals to a, I could have called it x, we just remember what the previous number was and increment a by 1. Theoretically, this should run either infinitely, or maybe we run into a crash once we overload because we run out of memory, or maybe there's something weird going on with the special numbers. Maybe we run into not a number. Does this stop? Is another question. And if it does so, then when does it stop and what value does a have? Well, for us, that's easy to find out. It has the value of 16,777 and 216. That is not the largest float we can store. We can easily test that. And we can tell we can still increase the number, but apparently +1 doesn't change the number anymore. Why is that? Why do we only have about 8 digits here? It's not always 8 in all conditions. And that has largely to do with what a float is. And also the reason why 0.1 doesn't exist. So let's quickly, this is not what I wanted to click, talk about what a float is. Most of us know the scientific notation of numbers, but I'll quickly explain it. 1.23e6 is one way of expressing a number, and that is the same if you translate it as 1.23 times 10 to the power of 6. And that's the same as 1,230,000. There we go. Figured out how to number. And the structure of this can be broken down in the correct terminology. That is the what we call a mantissa, and then an exponent, tissa, I guess. A mantissa and then an exponent. But we're still missing one thing, and that is the plus minus here. There's another position in here. We usually just don't write plus if it's positive, but it's implied. That is the scientific notation of numbers, and floating points are represented exactly the same way, except those two are flipped. And it's important to note that the mantissa in the floating point format assumes there's a 1 to the left for technical reasons. It gives you more precision. But then you could say, well, if you're only shifting this, right, so all the exponent does is shift this number to the left or to the right, depending on the base. And the base in programming is not 10, but a 2. And since all we do is shift the number left and right, how do we represent 0? And there's a special exception here, that is when the exponent is 0, the 1 on the left is not implied anymore. That's a bit convoluted. There's a bit more going on here. I don't want to really go into it, but that is in essence how it works, and the computer evaluates the same thing. And we can also see why this stops at a number that is about 8 digits large, because the mantissa for 32 floats 24 bits. And what number do you think is 2 to the power of 24? It's 16,777,216. That means all the numbers we're seeing here are of the form plus, or in this case, bit 1, but we're just gonna say plus 0 and then a. And as soon as we tick over here to a 1, sorry, we started with a 1 here. And as soon as we take over here to a 2, suddenly we shift this 1 to the left, and we don't have the bits to represent the numbers to the right anymore. That also means we only have a floating point always only has about 8 digits of information. It can have many leading zeros and many following zeros, but the sequence of numbers are usually only 8 long. I say usually because they're not in base 10, they're in base 2. So depending on how it folds and shifts, it could be just 7. Okay, that's interesting, and that also explains to us why we can add a 10 to it, because we shift this 1 over to the left. Now, in theory, we could write a loop that actually goes through all the floats using this logic by incrementing full integers. If we read back the exponent ourselves and multiply this here, and also shift this by the exponent, so that we make sure we are always matching these two up, that we basically have, we add this, that our adding number is basically this, where this exponent stays the same, like as where the exponent in both cases is the same, and we're just adding these two numbers together. Of course, we'll have holes, which is also a reason why it's sort of a really bad idea to use them for counting, because 16 million isn't that large of a number, and it is not unreasonable to have index spaces that are larger than that. So really, if you're using something to index, use an integer. Let's address another quirk of floating points, and that is that certain numbers don't exist even though we would expect them to exist. 0.1 is one of those, and I see a lot of professionals trying to use floating point numbers for actions that involve money. And under no circumstances should you ever use a floating point number if you care about the correctness of the result. Ever. Floating point numbers have many, many holes, and the fact that very common for us numbers like 0.1 don't exist is a huge problem. Now, if I run this, it'll probably, I haven't tried this, tell me that 0.1 does exist, but that is because many languages cheat by now, because 0.1 is such a common one, that they just round it and in quotation fix it, and the compiler can cheat a bit as well because it sees it's a constant, it's not used anymore, so it can just insert it as a literal. But if we make it just slightly more different by adding 0.2 to it, we can see, for example, that 0.3 certainly doesn't exist. Now I'm curious if what I'll do with 0.3. Let's just check. Yeah, see, you can see the cheating here. We know that something clearly went wrong because that is not 0.3, and there's a whole bunch of zeros in between here. So what's the reason for that? The reason for that is the exact same reason why 1/3 doesn't exist in decimal numbers, as long as we fix the amount of numbers or digits we have available. They're repeating. 0.1 is repeating in binary. If you calculate things where precision matters, you either need to use a special data type that doesn't lose precision at all and preserves that. That's very slow because it's all emulated in software. Or you can use fixed point math and just make sure you have enough digits after the decimal point so that you don't lose the bits that you care about. And those can represent then all the numbers. Like a fixed point with 3 digits trailing, it's just an integer shifted to the right by 2 positions, and it'll obviously have every single number in here. So it will have 0.1. Let's shortly talk very quickly. I'm not going through the math, just you can read up on binary division if you want to, why this is repeating. If you take any number to a negative exponent, minus y, then that is the same as 1 over x to the power of y. So In the case of decimal points, if x happened to be 3 and y to be -1, we would have 1/3, which is repeating, and the analog in binary. Binary division works exactly the same as base 10, you just do it in base 2. There's a whole bunch of extra things one can say about floats, like subnormal numbers and the special numbers like infinity and different zeros like 0 plus and -0. But I'm going to leave it here. Feel free to leave a read up on it. The standard of relevance is the IEEE 754 standard. It's sort of important that you know it, or that you at least have an intuition about it if you want to use floats. And sadly, not a lot of people teach that. They just teach you, hey, there's a floating point number. You can just write a decimal point and it works. It's not that simple. Have a good night.